All right, good morning. We have Shaowen Ma talking about BGP traffic engineering with SDN Controller.
Hi, morning everyone. My name is Shaowen, so I'm a product director for Juniper, Asia Pac here. Then today, actually, I got a co-presenter from Teng Xun, the chief architect. Unfortunately, he cannot make this trip. So today I will go through all the technical details here, then one or two late use case shared together with Teng Xun. Then later, if you have any question regarding the use case and so on, please reach out to Kin later. So today's topic will be, first of all, introduce some technology, then talk about the solution, then followed by the use case and the benefit for this solution, these things here. So actually, the network, the only not such important for traffic engineer might be in data center. Because of the lifespan, there's a lot of bandwidth there. But any service provider networks, as long as there's a fish topology here, there's always a requirement for traffic engineer. But the most important things here, the user, the subscriber, access to different content here. So previously, that's pretty much everything internet. But right now, you must redirect the traffic from a different destination. Go to internet directly, go to your local caching server, go to your own service provider content here. Then there's a lot of requirement to kind of redirect the traffic. How do you mapping the traffic here? Then a lot of cases, the content is not only inside IGP. You must extend the traffic engineer to BGP part. That means the BGP traffic engineer getting more and more important here. So today, actually, with Juniper, working with every web OTT customers, we're working together with some K service provider as well to promote this BGP egress traffic engineer solution here. The K solution, without this one, there's some traffic engineer method already in place, already deployed many years. But there's a lot of limitation here. Let me show you some limitation here. First of all, nobody can dynamically select which ASBR, which peering you can really want to send traffic to. It's all static configuration before SDN age here. Then there's also no BGP information between the different AS here. Those information never fully leveraged into this application-driven traffic engineer and so on. So the third one is the static tunnel configuration. It's always R3PTE configure from ingress, egress, and all the node can aware of those tunnels here. Then there's always a bigger requirement for the ASBR here. The ASBR router could be a very high-end router which can handle millions of prefixes here. So we are talking about 500,000 internet full prefixes. We are talking about a lot of VPN prefixes here. So makes this ASBR router is very expensive today. Then there's a lot of policy also deployed in the ASBR here. So it's not only from the edge customer tall router, from the BNG, from the CP equipment, the policy deployed, try to redirect traffic there. Then another one is you must deploy a lot of policy in ASBR to select which peer to send traffic to and which link you use. So there's a lot of issue here. So sometimes customer own. Sometimes the customer own this one, own this router, they own these networks. They don't own this ASBR router. Maybe different organization, you make calls and take times to really deploy any policy here. So with the SDN method here, all those problems will be addressed by this solution here. So first of all, we introduce SDN controller, which can monitor the network status and then can dynamically select ASBR routers. And also we use BGP loopback label unicast for peering and get the information from NetFlow, from BGP LS, from BMP, and so on. Then we always can do the dynamic segment routing selection. One of the beauty of segment routing is you do not need to pre-configure any tunnels. The tunnel come from the ingress node. The network infrastructure is very simple, and as long as you put different label stack, you can dynamically select which ASBR, select which path. So, and also in that case, I can show you that the policy on ASBR router is not much in this solution compared with previously. Both important things, the ASBR now can be a very simple router. So with those method, I can show you with this design, the ASBR can be a LSR router with a limited forwarding table or only MPS forwarding, that's it. So the foundation of this solution is based on the 3 drafts here. One from Juniper, and the other vendor also proposed a different method. I can show you what's the difference between these 2 methods here. Then, of course, this method can leverage segment routing as an infrastructure, but also can leverage any tunnel mechanical, like a VSLAN, like any tunnel as well. So the design philosophy for those BGP egress traffic engineers is quite simple here. Just because at the end of the day, you just want to redirect the traffic to different peer, different link here. So the matters, how do you recognize which peer, which link by this ASBR router here? So this ASBR router is actually assigned different label from different peer here. Then once he received the label, then he know that sent to different peer and passing through different network and so on. It's quite simple. Then, but the beauty of this solution, if you look at the IP packet payload here, from your network to internet and to the peering here, this MPS in your networks here. But the peering part can be IP only. So no need any, no requirement for any peering router. The peering router can be a very simple one, existing one, no need to upgrade at all. So what you want to do is some protocol upgrade to this router, and then they can talk to the WAN controller. So those guys assign label, then notify the route controller. The controller can push this label to the tunnel, through the tunnel from the ingress node. Then the first label is kind of a tunnel. This can be a VSLAN, can be a GRE, anything. Then the most important things, we leverage the BGP label unicast label here to assign to redirect traffic to here. So this direction, once you put the traffic into this tunnel, then reach to the ASBR router, there's no IP lookup. So that's a very important thing I want to emphasize here later. So the idea for this one is this controller monitor every link by NetFlow, by BGP LS, by BMP, or monitor any prefixes. So which prefixes is better, as longer AS pass or shortest AS pass, and so on. Then they can select which ASBR to send traffic to. So for controller, it's very simple. So this label, they put different label. The outer label will select a different ASBR. The inner label here, the loop, the LU label, will select which link, which peer, or which peer set, and so on. So the message for this one is kind of for this part of the network, you do not need to upgrade. That one is out of your control. Then for those part of the networks, for those ASBR router, you needed some protocol upgrade to support the BGP LU message, which is pretty much everybody in the market. Cisco, Juniper, Huawei, every vendor can support BGP label unicast. There's no need to enhance on the protocol part. And then you may use BGP link state information to carry the reserved bandwidth here. So for example, this one is always already reserved and a lot of bandwidth, not much bandwidth left. So next time, send traffic to this one, I will redirect traffic to here. It's always based on the policy, based on different rules to set those policy here. For those router, and those router can be really a BNG router, a tall router, tall switch. Also can be a server, like a Linux server with MPS protocol stack. No need segment routing, the full segment routing protocol stack, IGP extension, and so on, no need. Those kind of things. So as long as you can push multiple label to here, that's okay. Then some configuration from our Juniper router. Maybe other vendor has a similar configuration as well. So the idea for this one is a kind of this ASPR router actually set up two groups. One group talking to the controller, another group talking to the peer. For the peer part is just a BGP LEU, label unicast. Sorry, this one is a label unicast, and for this one is just a normal one. Then they mentioned for those peer, I will assign label for this one. So there's a egress traffic linear here to assign label for those link here. That's it. So from the peer point of view, it's just a normal BGP peer. So just give you some idea on how do you protect the network failure. For the link failure here is quite simple here. Because you already assigned some label here, then next time if you this link goes down, then you actually redirect your traffic to a helper here. Then you always can configure backup path sent to here. Then for those guys, you can do two things. You can do the normal IP lookup, send traffic to different peer, or you can assign this label here, assign a different label configured here. So this node can help them. So eventually, if you try to optimize your networks, there's different way to go. So phase one, maybe you don't want to kind of, you don't trust this solution a lot. So you actually try to deploy several router here, which have a full IP capable, but all others could be a simple router here. Which can lower down your cost dramatically here. Just leave one or two router with IP lookup capability here. That's the first method here. A second one is we need some enhancement on the router here. Then all the ASPR can be the LSR router, the link call solution somehow. Then those one you can protect the link, and you also can protect the node. When this node goes down, then you actually define a backup router, which know about the label unicast label and sending to different peer and so on. So that's a different method we can use here. I just want to highlight the solutions benefit for CDN, for peering, for service provider, for data center as well. So the benefit is something like this one. We all know that Google and other web OTT proposed a link call solution like 3-4 years ago. The link call, they actually changed the network infrastructure here. The network P router become an LSR router here. With this solution, you can easily to extend the link call to ASPR. So eventually, the network become more simpler here. So another layer, so the peering part, we talked to some web OTT in China, in worldwide. They are mentioned that there's 20 peering routers, and every router is very costly. And with this method, you can easily to migrate to a simple solution here. So the idea for this one is this part is MPLS lookup, no IP lookup at all. But if you're from internet to your networks here, that can be IP lookup, or can can be the MPLS lookup as well. If you really think about the IP lookup, then remember that some Broadcom chipset which can handle 128K prefixes. That's good enough for most use case because most service provider, their own prefixes, no more than 128,000 here. So in that case, with very simple boxes, simple solution, and you get the network-wide optimization, and the benefit is quite big here. So the idea actually coming from some mobile backhaul. So if you look at, you're familiar with a mobile backhaul solution, then you're familiar with a seamless MPLS or UMMT or different vendor have different name here. But the idea for this one is use RFC 3107 to kind of to carry those information across the different domain here. The BGP LU is already in the market. It's deployable for any service providers, any vendors box here for a long time. Everybody in mobile backhaul, Cisco, Alcatel, Juniper, any vendors, they support this one already. So from Juniper point of view, we only extended the EPE link here. So get rid of, put this node, one single node here, become a two node here, and only upgrade this one, and we can support this solution already. For other solution here is another draft talking about this solution. They actually need a BGP LS extension, the BGP link state extension to carry the segment routing labels. For their solution, they can only use with the segment routing tunnel. For us, which can be MPLS label or the VSLAN tunnels here. So our tunnel mechanical is independently with the BGP LU here. And for their solution, this segment routing here and segment routing across your network here. So from a protocol point of view, we do not need any protocol extension. Protocol development is all talking to any vendor's boxes here. Some minor enhancement on our boxes which can support this one. So from time to market, speed to market, then this solution is kind of a better choice for you. So then we also talk about a lot of web OTT guys talking about bringing in MPLS into the data center here. So we are actually talking to several customers in China, Tencent, Alibaba, and so on. Then we discuss about how we bring the MPLS into this inside the center, starting from the tall switch and so on, so to change this part. So the biggest challenge for this center is you always have a lot of transit ISP. You have a real customer ISP, then a multiple the DC gateway. So which DC gateway you want to select and which traffic you want to send to, that's a very important one because a different link here may cost you different money, a different amount of money per month and so on, and different peering condition here. So it's very critical for you to select the egress point and select to send traffic to which peer here. So that's actually same situation as we talked before. So here you actually use the metadata to select the different peer here. Then you always use a tunnel encapsulation, which can be VSLAN, which can be segment routing, which can be GRE as well. Then, as long as you actually from the server here, software router here, you put the traffic here, then you assign different label, BGP LU label here, then they can select a different peer. So the tunnel get rid of the tunnel header, then you get this BGP LU label you can send to different peer here. The return traffic you also can be controlled. Then in that case, the metadata not stand for the peering, but stand for the virtual machine. We actually can assign every virtual machine a label here. In that case, from an ASPI router, you know that which virtual machine you send traffic to, then you actually associate these labels. And from span switch, leaf switch, top switch, even to the server, then you get rid of the tunnel, then you can send the traffic bi-directionally here. So another, just give you one more example on the CDN peering. We do have other examples, like how do you mapping the PPPoE subscriber into different peer and so on. But given we don't have a lot of time here, so I just talk about briefly on the CDN peering part. So for this one, it's really control plan, the data plan separation concept here. The ASPR router, previously, you have a full internet forwarding table, like 500,000 and so on, which make this ASPR router is very, very expensive here. And also the link here also very expensive. But this time, you actually sending the routing information to controller. So controller can support millions of prefixes. But the real forwarding on these boxes is less than 128K or less than 500,000. Then it's LSR only forwarding. Then all the routing information here coming from the controller. Controller know that which CDN server sending traffic to, and you, as any optimization tools, you don't need to optimize every prefixes. You always kind of look at the situation in your networks. Then you select some prefix groups, some AS numbers, and then you kind of redirect traffic to the not so crowded peering here. So the solution is somehow like this one. Talking about one of the customer, Tengxun, we discussed with them several times, and they really like this solution here. One of the key pain point for them, there's no global BGP traffic engineer previously. And previously, they always use RCPT static tunnel, try to direct traffic from one end to another. And the peering traffic grows so fast. You know, all the videos, all those things from Tengxun. Then they want saving the capex on the peering router here. So the problem here is somehow like this one. And after we discuss, here's a plan. We actually working together with them, try to define any rules, policy, and try to select a different peering here. So the router here will send in the BGP LU message to the controller and get the link state information here. Then the different video server or the web services can send in traffic to different ASPR and select a different peering solution here. So from Tengxun is actually, they get benefit from this solution. First of all, global BGP traffic engineer. Second one, there's no policy on ASPR. The policy is starting from the ingress router only here. Then there's a potential capex saving on the ASPR router as well. Then Tengxun is mentioned to us, the all-in segment routing. So eventually, Tengxun's WAN networks, DC WAN network, will be segment routing, trial starting from this year. And the all-in global traffic engineer, BGP traffic engineer, and so on. Yeah. So that's the use case here. So we're always talking about SDN. We're always talking about those kind of how do you optimize your network traffic and so on. So eventually, what we think, instead of everybody talking to individual boxes to do the scripting, Python, Ansible, and so on to access those box level, you actually need a layer of a controller. Which controller can get two jobs done? One thing is to get the network information. Another one is to push the configuration, push those policy down to that. But the most important thing is the application matters. The application on top of those controller, which can handle all those information from BTPLS, BMP, PSAP, and so on. So gather all those informations and define the business rules And then, as long as you can push the business rules down to your networks, that's SDN-controlled networks. So today, we discuss about the SDN controller together with BGP traffic engineer. You can see here, we're not gonna to replace any router in your networks. It's not a greenfield network we try to build. It's always a protocol enhancement and plus some kind of tweaks. And then introduce the SDN controller can have a very good benefit for your networks. So if you feel this solution is good, talking to us, and any service provider, CDN peering solutions, any customers, let us know any information on this one. So here's a summary for today. So, so thanks a lot. That's all from my side. Any questions? For sure.
Next up, we have Pete Moyer. OpenFlow, what is it good for?
Everyone's favorite topic, OpenFlow. So my name's Pete, I'm with Brocade. I'm going to talk about OpenFlow, and actually I'm going to talk a little bit, hopefully, actually, can everyone hear me? Hopefully talk a little bit differently and change the conversation around OpenFlow and kind of the way you might think of OpenFlow. So I'm not going to talk about it in the typical use case that everyone thinks about, although I'll cover that as background material. And I'm really covering kind of network services, so using OpenFlow for a network service instead of network plumbing. It's kind of awkward here. I'll look at these. So here's the agenda. I'm sure everyone knows what OpenFlow is, so I think I have like one slide just to go through the revisions, just to kind of catch everyone up. I'll talk a little bit about the OpenFlow deployment examples that are out there today, so kind of prove that it is deployed, probably not at massive scale, but it is deployed. But my talk, again, is really about the other use cases for OpenFlow, and that's kind of the focus of my talk, and then a conclusion. So a little refresher here. Hopefully no one's data center looks like that. So James Hamilton, so a lot of people say that this is kind of where it began. So he's the architect or something at Amazon, and obviously what he was talking about there was the network was very rigid and brittle and configuration intensive, and so they did a lot of automation, right, for the Amazon cloud and kind of SDN. I don't want to say it spawned out of that, but part of the goal of SDN is to make networks agile and programmable, just like the previous talk. And then the other reason I put this in here, what's this got to do with OpenFlow? Nothing, but it's kind of a cool slide, I thought, so I put it in there. So here's one of my favorite slides. So SDN, what is SDN? If you ask 10 people, like 3 years ago, you probably got like 10 answers. If you ask 10 people today, you probably get, 1 or 2 answers. But this definition is right out of ONF. So a network in which the control plane is separate from the data plane. So that's an ONF definition of SDN. Obviously, SDN means a lot more than that. So obviously, ONF is a big push of OpenFlow. So a lot of folks, previously thought that OpenFlow equals SDN and vice versa. It's clearly not the case, right? You can do SDN without OpenFlow with BGP. So the picture on the right, so that was kind of the vision of the ONF and what I call some of the academics or the purists, if you will. Take that control plane, stick it on a controller, move all the intelligence up to a logically centralized control point, and then you just need a simple protocol like OpenFlow to program the forwarding tables of the switches. So there was, some benefit of that. Some of the use cases I talk about that are deployed kind of do that, but that's fairly unusual. And what I'm really going to talk about is not doing the ONF version, but keeping the control plane on the box. I'm not talking about taking the control plane off the box and basically building networks with OpenFlow. My talk is slightly different. It's keep the control plane on the box, have additional functionality in the controller, use OpenFlow to provide a network service. And here I show other APIs, that could be netconf or what have you. And then I stole this, I think, from Yakov or someone, distribute what you must, centralize what you can, right? So the purists, they want to centralize everything in the controller. And, in my opinion, they're kind of going too far to one side of it. Right now, everything's distributed. Distributed protocols work, right? OSPF works, BGP works. If it's not broken, why try to fix it? Why try to centralize routing protocols that work in a distributed manner? So distribute what you must, centralize what you can. Now, if you can centralize some applications and stick them on the controller, or some functionality and stick it on the controller, yes, do that. And then you can get a network service out of that. But this is kind of a hybrid model, and I actually have a hybrid switch there at the bottom. Right, so that switch is an OpenFlow switch. It also supports IP and BGP and MPLS. So, it's not that you need to forklift your network or move away from those technologies, but look at OpenFlow as a way of providing a new service, or maybe solving a problem in your network today that you can't solve with existing tools. So a little bit about version history. I won't cover this in too much detail. So obviously OpenFlow has been around for a long time, 2009. I mean, that's like forever in internet time. So version 1 wasn't that useful, right? All the switch vendors and controllers supported version 1 when it came out. Very limited functionality, v4, basic matching actions. A lot of people, used it in the lab, but it wasn't really deployable because, it didn't support like v6 and MPLS and QoS and things like that. So down at the bottom there, version 1.3 is kind of where the industry kind of converged on, and that's where we kind of are today. So most vendors, switch vendors that support OpenFlow and controllers are all on 1.3. And that includes everything else, so MPLS, V6, et cetera, QoS, and things like that. So 1.3 is useful, can do useful things. I'm going to talk about some use cases for using 1.3. And then you can see, it's still evolving. There's 1.4, there's 1.5. 1.6 is supposed to get published like anytime now, sometime this year, which includes tunneling. It's kind of interesting. And they're already talking about the ONF, what's next? Is there a 2.0? Is it OpenFlow next gen? And then along comes something like P4. There's a link there, you can check that out. That's basically envisioned by some of the same people who kind of envisioned OpenFlow. So there's folks already kind of looking ahead saying, what, OpenFlow was useful. It lacked a bunch of stuff. Rather than trying to add more versions and features to OpenFlow, maybe let's try something different. So that's what P4 is about. We'll see where it goes. So what are some examples? I mean, is it deployed? Some of my, OpenFlow supporters here, they always ask me that. So everyone knows about Google, right? So Google has their inter-data center backbone. It's 100% OpenFlow. I guess you could say they were the first. So they did prove you can deploy this, at scale. I mean, it's not massive, but it works. Everything's centralized. So their switches, we probably all know they built their own switches. Those switches don't have a control plane. I mean, it has some basically boot code, but all the control plane lives on the controller. So you can see things like that, and they have their own controller. Matter of fact, their controller now not only controls the network switches, but the VMs and the data center and the WAN and everything. So they're really converging on a kind of an SDN model. The previous one, where the control plane lives on the controller. So they proved it works. Now, of course, they're Google, so they're kind of special. Now, what are the benefits? So I stole some of these from one of their websites. I added a few. But obviously, with a centralized control plane, you kind of decouple software and hardware. So now you could pick the hardware features you need, and you could pick the software features you need, rather than buying a switch from a vendor and you kind of get everything. Maybe you're not going to use MPLS, but you bought a box and it has MPLS code in it. Maybe you don't want that, right? So this allows you to kind of pick and choose. And then it decouples innovation. That's really important. So now you can innovate in software, particularly in the app layer, right? You could add apps on top of the controller at much, much rapid time frames, within weeks. And if your network supports a unifying API, you can actually take advantage of that and enroll that into your network in a matter of weeks, rather than waiting for a network vendor to put a feature in that takes 18 months. So deterministic, global view, really important. What's also cool about this, I thought about this because I saw the modeling talk earlier, which was really good stuff. And with this, rather than building a model of your network, right, which is important, everyone should do that, you actually have the network in software already. So you have it's a model, but it's the real network in software. You kind of have it there. You could take a snapshot of that real time. And so with the global view and with these efficiencies, I mean, you've probably read the press, right? They're running links supposedly at 99.9% utilization. I mean, that's unheard of, right? Most service providers run 50%, start looking at upgrades at 50, maybe 70. I've heard some as low as 30 because they want to handle failovers and things like that. They're running their network at 99%. So that's pretty impressive. Other examples. So Internet 2 is a US-based research backbone. They're pretty kind of early adopters. They deployed MPLS a long time ago. They deployed IPv6 a long time ago. They basically built a 100 gig OpenFlow network probably 3 years ago. So here's another example. This is deployed 3 years, and it's similar to the Google model. There's OpenFlow only switches that are basically building layer 2 paths today. So they're not doing other functionality. It's a pure OpenFlow backbone. What's cool, if you get the presentation, you can go to this link. They actually have this router proxy site that shows the nodes on their 100 gig backbone. So as you can see, it's Juniper, it's Brocade. And then what's even better is you could do a drop-down menu there. So I'm doing a snapshot of a show OpenFlow flows on a Brocade MLX. So you can actually go to Internet 2's website, look at the routers that are in production, look at the flows that are installed. It's kind of cool. They actually allow you to do that. So a few more. BGP Free Edge, so NTT, Robert Razuk and those guys are kind of building that. NTT has made some talk at ONS about deploying OpenFlow. And then I don't know, is anyone here from RNet? So they did something similar to the BGP Free Edge, and supposedly that's in production. It's mainly for BGP peering, so it's kind of a limited scale, limited deployment, kind of solve one problem, but at least they're testing the waters with OpenFlow. It's not a network-wide implementation like Internet 2 or Google. So look at some other examples. Where are they? That's the question, right? So OpenFlow has been around for 5 years. There's like a handful of examples. So, you know, interesting enough, the title of my talk was going to be, is OpenFlow dead? But Dave nixed that. He didn't like that talk. Because, you know, a lot of people are like, well, OpenFlow has been around for so long. Okay, there's Google, there's Internet 2, there's a few other small use cases, but, you know, why isn't it deployed? You know, is it dying? Is it dead? Another point of view, the demise of OpenFlow has been greatly exaggerated. So I'm going to talk about using OpenFlow not to build networks, which are those examples, because, you know, that's a whole separate discussion. I'd love to have that with you over beers. That's many hours. We can argue about that, whether it's useful to build networks. I'm going to talk about using it to provide a service, just a different way of thinking about OpenFlow. So I just grabbed some SDN use cases. I'm not going to talk about all these. I'm going to cover some OpenFlow use cases that are going to be, you know, obvious uses of OpenFlow. And then hopefully I have a couple interesting ones. I even have one that combines MPLS for the MPLS guys in here. And then I have a kind of a packet capture use case. So some of these will be blatantly obvious. I think hopefully there'll be a few at the end that'll get you thinking about OpenFlow. So DDoS mitigation, right? I mean, I probably saw 5 talks here. Every time you go to a nanog or something, there's something on DDoS mitigation. FlowSpec, great example. DDoS is a huge problem, and this is just an example of, well, you can actually do DDoS mitigation with OpenFlow, right? Because OpenFlow, it's kind of like an ACL, right? You match on something, and it's very granular. Layer 3, layer 4, interface stats. You can combine layer 2 plus layer 3. So it's layer agnostic. You can do match VLAN blah plus IP destination blah plus TCP port number X. And then do something with those flows, if you will. In this case, you have packets coming in, so the border router. So this is another example of where you can incrementally deploy OpenFlow, right? You can just stick it on that border router. You don't have to go and flashbang your network and have OpenFlow everywhere. So that border router, in this example, he's doing SFlow, could be NetFlow, right, up to a collector. There's an app up there that's combining or matching the SFlow samples with some type of profile, maybe a known DDoS attack. And then once there's a match, well, the DDoS attack is in progress, he basically pushes an OpenFlow rule and says, throw those packets away, right at the ingress interface. Oops. Yeah, right at the ingress interface. Now, that doesn't protect the uplink, right? So this is kind of deployed internally in the network. The other thing that's interesting about this is, although you could do this with FlowSpec and you can actually advertise it and then have the packets drop upstream, we have a lot of enterprises who are interested in this use case, universities, because they want to protect the campus edge. And typically those boxes don't have BGP at all. So now they can protect the internal edge and not just the internet edge. You could basically do your entire perimeter with this. And it's very simple. I mean, you can write an app like this in a matter of days. And again, deploy it on one box. You don't have to deploy it on, you know, your whole network. So this, obviously, it says L2 through L4, so this really works for volumetric attacks, right? OpenFlow only looks up to layer 4, so this doesn't protect you from very advanced signature attacks, layer 7 attacks. But you can combine this with a advanced security solution, like perhaps from Arbor, right? That's another use case is, rather than having some very expensive appliance that's doing, layer 1 through layer 7, you can offload the nasty high volume attacks from that expensive appliance and just drop those in the network. And then you let that appliance do what it needs to do, right? So it's kind of an offload effect. So there's a lot of uses for this. So that one's probably an obvious use case for OpenFlow. Oops, did I miss one? Okay, here we go. So flow metering, right? OpenFlow has the meter function. You probably saw that earlier. I think that was in version 1.2 or something. And again, just like the other use case, these are hybrid switches, right? So these switches run IP, and they also support OpenFlow. These are not OpenFlow only switches. So it's very simple if you look at that, right? He's doing S-flow up, just like you saw previously. Maybe there's certain flows that you want to block. Maybe you're an enterprise and you don't want, or a university, you don't want your students, downloading whatever. So you can match that, create a profile and says, when you see these type of flows, just rate limit them. Very simple function from OpenFlow. So it's the same thing. He pushes the parameters to a controller. I show Open Daylight, kind of, that's the open source one, so stay vendor neutral here. And then he pushes a rule that says, when you see this flow, rate limit it. Very simple. So this is another obvious use case. We have customers kind of interested in doing this, again, at the edge. Even like regional service providers who want to rate limit the edge. Instead of doing really complex ACLs and PBR rules and things like that, do it right here in a GUI. Configure a profile, hit click, it's done. So research and ed networks. RNet was one of those, these guys are typically ahead of the game. They've been looking at OpenFlow for many, many years. In the US, Energy Sciences Network came up what's called the Science DMZ, and I'm sorry for any vendors that sell firewalls here, but they came out and said this high capacity network used to sit inside the campus. And what they found is as researchers collaborated with other researchers, they were pushing huge data sets. And this firewall, this enterprise firewall, was a huge bottleneck. And so what they were forced to do, they came up with the Science DMZ concept. They were forced, and they're deploying this, even in Australia as well. They're taking this high performance network outside of the firewall, and they're connecting it directly to an upstream transit backbone. And they have to do that because the firewall is such a performance bottleneck. Now, I looked at this 2 years ago when I saw this. I'm like, what about security? So, yes, you solve one problem. You have high performance, but now you just created a massive security problem, in my opinion, right? So they're deploying this. And so what we came up with, well, don't do that, because that could be harmful. Why not use SDN? So this is just another way of looking at it. So use SDN, keep everything behind the firewall, and then you could say certain trusted high-capacity flows, right, based on your security policies, bypass the firewall. So it's a redirect action in OpenFlow. So you push that to the OpenFlow switches and say, for these flows, redirect it around the firewall. So the rest of your network is still protected by the firewall. You're not exposed. And so now they're starting to deploy, my slide's a little messed up there, starting to deploy SDN to solve this problem. It seems like an obvious problem, and it's very simple. So the first use case was, OpenFlow action of discard. Second one was a meter, and this one is just redirect. It's like a PBR rule. Elephant flow management, again, same thing. So hybrid switch, some flows go forwarded normally. You could remark QS, right? You could reset the QS values, or you can say, man, there's certain flows that I want you to redirect, and maybe to a different set of paths, right? So there's very simple functions that you can use OpenFlow, and you can use it on 1 or 2 switches or 10 switches. You don't have to deploy it across your network. Or you can keep doing this. So we see some redirect actions here, some PBR rules, and I'm sure everyone loves ACLs. Interesting enough, I was at a conference, I don't know, a year or so ago. There was a large financial company, like B of A large. He said they had 10,000 ACLs deployed in their network. 10,000. And once we're all engineers, once you put an ACL on a box, Do you ever take that ACL out? Probably never. And so over years, that config gets, 20 pages, 50 pages, and there's gazillions of ACLs, and then you have to troubleshoot a problem because someone mistyped an ACL, and now you're asked to go to that router and figure out, what's wrong. I mean, this is insane. So you could do this with OpenFlow, right? OpenFlow is like an ACL, and the action, if you want to do a PBR rule, it's a redirect. And so now you can have a centralized application that kind of stores, if you will, all your global ACL policies, your forwarding policies. And then you could pull the rule out really quickly. So you can normalize the network. So for my MPLS friends, so what about OpenFlow with MPLS? So again, my talk isn't about building networks with OpenFlow. That's an entirely separate discussion. My talk is about using OpenFlow to provide a service. Here's a very simple use case where you can have, maybe you have multiple LSPs, gold, silver, bronze for different priorities. And at the ingress, LER, you can have an OpenFlow rule that says, for these type of packets, voice over IP, video over IP, put it in LSP blah. So it's a redirect action. It's like a PBR rule. But you have the matching granularity of OpenFlow, which is very, very granular. So you're not just matching QoS bits into an LSP. You have everything in that header available to you. And it's very simple. And again, it's the same app. Same app sitting on a controller. He's just pushing an OpenFlow rule that says, when you see these flows, put it in LSP 10. So you can call this kind of application-aware TE, if you will. You can also do metering, right? So you can meter traffic into the LSP if you want, and then push it in the LSP. So there's a lot of uses for OpenFlow. And these are kind of obvious. But there's more. So everyone does packet capture. The current mode of getting packet captures, which is getting network visibility, is very cumbersome, and we've all done it. The old days you used to have to deploy someone with a sniffer, go stick that sniffer to port blah, go do a span on the router or switch. Now you have that sniffer getting all the packets from a certain port. It has to do massive filtering. As we get to 10 gig and 100 gig, that's no longer feasible. So now you go to that switch and go, well, don't just span everything, just mirror certain flows. So now you configure this very complex, per vendor, proprietary ACL type of functionality to say, just mirror these flows. I'm troubleshooting an application problem. I just want to look at this flow between these two hosts. So now you go to the box and you configure very complex policies to do that. So that's kind of what I just talked about here. The current mode of operation is very cumbersome. It's very difficult. A lot of folks are doing what they're called visibility networks, where they're actually deploying switches just for visibility, and they're tapping off their existing network into this visibility network. I mean, that's a huge cost. Why not use OpenFlow to solve that problem? It does it very well. It's dynamic. Again, you could actually push a rule into the network to do something, and then when you're done with that, you pull the rule out. All networking vendors support span, but again, it typically mirrors everything, so now you need to filter things, or you can do very complex ACLs, right? That other example. Very, very limiting, very complex. And everyone has this problem. Everyone needs to get visibility of their data plane traffic. So again, look, it looks the same. Very simple app on a controller. This OpenFlow rule is a kind of a mirror function. So in this case, rather than redirecting or dropping packets, the bad packets are actually just taking a copy. So the normal forwarding continues unaffected. You're just taking a copy of certain flows, matching granularity of OpenFlow, and say, just mirror this one flow. And if you combine this with the previous use case, you can say, mirror it out a port. Maybe you have an analytics device there, but more than likely, your analytics devices are somewhere in a data center. So now you basically mirror it into a tunnel. Could be an LSP, could be a GRE tunnel, could be an IPsec tunnel, right? So you combine it with that previous use case, and now you have this remote mirroring, per flow mirroring capability using SDN. You're not configuring span ports, you're not doing network taps, it's inline. OpenFlow, when you push rules into a switch, typically they're done in hardware, so you can do this at line rate, at scale. When you're done, you basically deactivate the profile in your app, and it pulls that mirror rule out. So now you've normalized the network. It's very cool. You can have a farm of analytics devices and have different flows go to different devices. voice over IP for performance and what have you. So to wrap up here, so it is deployed. Most people, when they think of OpenFlow, right, they think of building networks with OpenFlow, and that's why I think there's a lot of doubters saying, well, why would I do that? I have MPLS. So that's kind of the first part, right? So you're building a network using OpenFlow to forward normal traffic rather than using IP or MPLS. And again, we can talk about that over beers. That's not the point of my talk, whether that's useful or not. What I'm trying to say is think of OpenFlow differently. Rather than trying to build a network with OpenFlow, keep your existing network, IP, MPLS, what have you, but put OpenFlow on top of it to provide a service, maybe to solve a problem. You can actually even sell the service, right? There's a customer recently who's selling DDoS as a service, and he just deployed a controller, and he's doing DDoS on these border routers. Very simple. It's also could eventually, I think it will, replace ACLs and PBR, right? So the days of configuring those complex ACLs, hopefully they go away at some point. And OpenFlow is a really good tool for doing that functionality without all the complexity. And when you provide a service with OpenFlow, as it says here, you're actually only touching interesting traffic, right? You're not trying to plumb the network with OpenFlow. Let IP do IP stuff and use OpenFlow for interesting stuff to provide a network service. And again, some of the use cases seem obvious, but they're operational. They actually solve real problems. These are not theoretical. We have customers who are actually deploying this today. So hopefully, as more people think of OpenFlow as providing a specific service, kind of like a tactical solution, it will get more widely adopted. Rather than trying to think of, well, I don't want to build my network with OpenFlow. Well, I'm not saying you should or shouldn't, right? It's up to you, but use OpenFlow to provide a service or solve a problem. That's what I had. Any questions? There's got to be questions about OpenFlow.
So Reza Shahab, Nokia. Very interesting use cases. You had the slide there that had all the different versions of OpenFlow and where they're at. In terms of these use cases, how much of this actually gets captured in existing versions of the spec, and how much do you think needs to be done or can be handled by vendor extensions?
Yeah, so most of the use cases, probably all of that I talked about here, are in 1.3, right? So everyone's on 1.3. These are all solved with 1.3, because with 1.3 you get MPLS labeled, you get QoS, you get redirection, mirroring, rate limiting, you get all that. You could do V4, V6. So some of the other stuff, like it's coming out in version 1.4 or 1.5, I'm not sure how useful they are, and it looks like, just like everyone skipped from 1, they went to 1.3. Not a lot of people did 1.1 and 1.2. It looks like the industry might go to maybe 1.5 because there's some useful stuff coming, but we'll see. It's TBD. And, and again, the industry just might skip and go to something like P4 as well, right? I mean, we'll see.
Okay. Thank you.
The ones I talked about were all in 1.3.
No more questions?
Okay, thank you.
More seats here if you want to come and sit down now. Good. Next up we have Alastair talking about software-defined WANs.
Right. So my whole schedule has been thrown off because we're a few minutes early. I was going to start with good afternoon, but now I've got to just revise it, go to good morning. Because we've got a couple minutes going here, hopefully we'll get out early for lunch. I hate being the guy that stands in between lunch and all of you. I'm AJ. I'm from Nuage Networks. We're a part of what is now Nokia. Previously, we were a part of Alcatel-Lucent, so now we are Nokia. I'm going to talk about software-defined wide area networking, and actually it's kind of cool to come last in this session because it's going to build a little bit on what Pete and Shaowen have talked about. I'm not going to go and dig into the nitty-gritty too much of the OpenFlow and how it works because Pete's just done that, which is actually really awesome. And I'm going to talk about some use cases that can pick up on OpenFlow or other programming techniques. For those that have not heard of SD-WAN before, it's the software-defined wide area networking concept. Last year at APRICOT in Fukuoka, I talked about it as well. I think at the time I was still referring to it as software-defined VPN, but it's largely the same thing. It's about a new approach to wide area networking, effectively focused in the enterprise case. Now, we could say that it's service provider centric because it could be used by a service provider to offer a product or a service to their customers, or it could be used by an enterprise themselves. It could be part of a packaged up product, for instance from us, or it could be something that's build your own using things like Open Daylight and OpenFlow and Open vSwitch. There's many ways to tackle this. But what's going on right now in the industry is a big rethink of how the enterprise network should operate. We've been doing MPLS VPNs and other types of VPNs for 15 or so years with not a lot of change since what was 2547 came out. We've revised things, we've improved scale, we've gone to BGP labeled unicast, etc. We've made our networks bigger and bigger, but the fundamental concept of a layer 3 VPN hasn't really changed. We also have problems in managing devices. On the end of every PE-CE interface, there's a CE router, and some of these networks are very, very large. Pete just mentioned one of the big financials in the US, and that same financial has around about 7,000 branches in the USA. Every branch has 2 CPEs at it. That's at least 14,000 CPEs that have to be managed. So a lot of what enterprises are looking for is not just about, oh, let's use a new technology, let's add something to the network, but let's also get some operational and management advantages. And let's be a little bit more IT-centric. Let's use things like Ansible or Puppet or Chef or something else to really automate our configuration management. And I loved the example of ACLs because in the enterprise space, ACLs are a nightmare. They're a nightmare in the carrier space. And this is really a way we can look at making this more efficient. So digging a little bit more into SD-WAN, there is an organization called the Open Networking User Group, or ONUG, that has working groups in it. And there is an SD-WAN working group. And this defines use cases, test plans, and in the case of SD-WAN, a set of requirements here in the blue box. And these were sort of boiled down from enterprises with vendors involved in supporting the discussions and the conversation, and basically came out with the sort of the Big 10, right? Where we're looking at things like we want to use multiple WAN links. We want all active coming out of a branch location. And those links might be a mix of public and private. So I might have an uplink from a service provider into an MPLS VPN and an uplink from an internet service provider just over the internet. And I want to move traffic dynamically between those links based on the type of traffic, the confidentiality requirements of that traffic, or maybe the performance of those links. I want to be able to make everything secure, so I need to be able to do IPsec or some other confidentiality on the data plane as well, and I need to be able to do that at scale. If we're talking about 50 sites or 30 sites, maybe I can manage this and manage key exchange kind of manually or with Ike, but if I'm talking about 5,000 sites, 10,000 sites, I need to be able to centralize and manage that a little bit better, but I still want to be able to do very fast key rollovers. So I don't want to have to go and touch all of these devices to roll a key. I want to do layer 2 and layer 3. I want open or at least accessible APIs northbound so that I can interface other systems, which could be part of my cloud environment, part of my network management infrastructure, etc. So I can get information out of the network or put configuration into the network. And ACLs are a good example. If I push out a new application, and if you're in the enterprise space, maybe Microsoft Lync or Skype for Business is something that you're deploying. I might have to change rules in my network to allow that application to work. Well, traditionally, I have to go and touch these huge ACLs on every part of my network and modify them. Now I can go into a centralized platform and say, hey, change all of my ACLs on all of these devices that are grouped somehow. Or even more, I can interface the application into the platform that's managing, so when Link goes to a new site and it has some bandwidth requirements, it can say, hey, I'm deployed at the Auckland site, and I am an application that looks like this, and I need 10 megs of bandwidth, and start asking the network to change itself. There's a very heavy focus in ONUG on virtualization. A lot of their initial work was cloud and data center oriented. And this means that we're looking at network virtualization. I'll talk about that in a bit more, but it also means we're looking at virtual machines. So one of the requirements was any new SD-WAN function must be available physically or virtually. So any infrastructure needs to be able to offer both types of form factors. And it's really driven by the concept of, changing my network, maybe operationally. I have a big ops problem. Just software life cycles on 10,000 or 15,000 routers in my network is very challenging to manage. If I need to roll out CPEs or software to those CPEs, I have to find maintenance windows, I have to push software, reboot them at a time that's convenient, and accommodate upgrade failures. It could be around the financial aspects. I want to reduce the amount of money I'm spending with my service providers on MPLS bandwidth. It could be efficiency. I want to be able to delegate control of some aspects to regional ops teams or even local ops teams. And it could be new capabilities, virtualized firewalls, pushing ACLs deeper into the network rather than centralizing them. Could be offloading internet traffic at the branch site rather than carrying it back to the hub. So looking at it in a picture format now, I have a traditional network. My headquarters is Auckland, Wellington and Christchurch as my branches. I've connected them to the internet and to a traditional MPLS WAN. What I can do is I can go and deploy a centralized policy and control platform. So this would be my SDN controller. That gives me this approach to deploying config. Now, when we talk about SDN, we often do just talk about, yep, I have a central controller. We need to back that controller with what it needs to program. I need a database or a policy engine as well. I don't want to just move the control plane somewhere. So I need something which is a bit smarter and is able to understand policy. And so this is where we see a very interesting mashup of what we've done in mobile networks or broadband networks with policy infrastructure, where we see centralized control, and we also see the scale of the internet all coming together. And that gives us the ability to automate branch and service orchestration. We can then overlay services on top. So we get this SD-WAN enabled network. So this is about tunneling, so different end caps. We're not relying on the native underlay network. And we can coordinate that all from the controllers. So we can push down, if we needed to, MPLS labels and use GRE as the data plane. We could use VXLAN. We could use IPsec. And then we have site-to-site network connectivity. This also gives us the ability to do some smart things at the controller, because we can start to see, oh, well, the Auckland site is hitting 80% load on one of its uplinks. Let's move some traffic off that uplink. So we'll go and tell all of the branches that what we need to do is move that traffic. And we can do that within bounds. Maybe we can designate Wellington as a high priority branch, so we'll try and keep its traffic as much as possible on the MPLS link. But Christchurch, we could move its traffic over to the internet tunnel. And so one of the other things that I want to sort of emphasize is network virtualization is not really new, right? If you go back to sort of pre-internet, or at least before I was really in the industry, the optical networks were our transport and our service. So we were buying point-to-point links. They were PDH, SDH, etc. These days, they're WDM wavelengths. At some stage, they were ATM. We overlaid IP on there as well. As the internet boomed, we built these IP backbones, and we were running IP. Then we needed to scale those networks a bit more. We wanted to add services, so we put MPLS in there as well. And so the network virtualization concept continues on. In the data center, we've seen overlays become very popular, which is just about running an NCAPS over a network. Commonly in data centers, you'll see VXLAN, but you might see NVGRE, you might see other platforms and NCAPS as well, even MPLS itself. So it's not a new thing. What we're doing is we're just changing where the service is instantiated and where the transport is. So we're decoupling service from transport, and this becomes quite key. So we continue to abstract. Now, you might be thinking, if you've been looking at this and thinking about CPE-centric changes to your network, well, how is any of this different from a virtual CPE? I've been looking at that a lot. So vCPE does mean different things to different people. So for some people, it sort of means the box here on the left, talking about taking a CPE, running it as a virtual machine in a data center, and maybe backhauling traffic from the customer site to this virtual CPE in the data center over a layer 2 tail. For other people, it means the box on the right, an x86 system at the customer location running, again, virtualized functions. So both of these can be treated as vCPE. But vCPE is really about just the CPE paradigm. I'm continuing to do the same thing. In some cases, I'm literally taking an existing CPE and I'm turning it into a VM, and that's about it. I've maybe run it on commodity hardware. Maybe that's cheaper, maybe that's faster, maybe it's about the same. But it hasn't changed the way the service works or interacts. So it's a bit same, but a little different. And it's not really necessarily taking advantage of any of the management or automation improvements or the control plane improvements that we can get. And so this is where I'll briefly pause. For those that don't know me in the room, I was very, very skeptical about SDN about 6 years ago when SDN started to boom. And so Neil is laughing in the back there because he was around at the time, as I was saying, it'll never take on, right? Why would I want to distribute or centralize what is very distributed, very scalable, very reliable? I was very, very skeptical. I could see value in data center networks and cloud networks, but I could never see the value prop for service providers. Then I started working with our teams that came up with this idea in-house, and then, of course, with the broader industry. And I said, okay, yeah, now I start to see it. It's not just about centralizing the control plane at this point. It's about taking my existing network, adding some more value, and getting some more management and orchestration and automation. So let's do things better. Let's do them faster. Let's get more control, better visibility, rather than just saying, hey, let's move the control plane. And I think that's really key. For a lot of people who have been skeptical, as I was, and there's certainly a few people in the room that find my change of opinion quite amusing. So this evolution is being driven by this control and flexibility and cost. And I touched a bit on this already, but hybrid transport is really interesting for a lot of big enterprises. So this is mixing and matching MPLS and other dedicated underlay services with typically the internet. And that's come about because the internet has become good enough. New Zealand is an excellent example of that, with UFB kind of widely available. If I have very high-speed broadband that's reliable and just pretty much available anywhere I want to go, then the internet becomes a very good transport layer. But more and more this is happening worldwide. In the US, you see Comcast, Google Fiber, Verizon Fios, etc., offering extremely high-speed broadband services at very low cost. And so enterprises start to think, hey, I'm still paying $1,000 a megabit for MPLS service, or I can go and pay $1,000 and get a gigabit, or even less. Why am I doing this? And sometimes this is because I want to have one throat to choke. If it goes wrong, I want to call up my service provider and say, hey, it's gone wrong, you're at fault, give me money. But sometimes I just want to realize some cost savings. And there have been some enterprises that have given some pretty interesting presentations publicly. Coca-Cola is one of them, there's several others, and talked about their evolution to hybrid. In one case they said, well, our cost didn't go down, but what our performance went up, because we were able to offload internet-bound traffic directly at the branch. We were able to move traffic that was low value, like backup traffic, email traffic, off onto the internet links. And that gave us a real business case for deploying this. And then the management, et cetera, benefits came in as well. But really the cost savings kind of make it so and drive a lot of business cases. But also, the fact that everyone's got so used to putting things in the cloud. If I'm a CIO somewhere and, personally I'm using iCloud and Google Docs, etc., I'm kind of used to the internet at this point. I'm no longer afraid of it. And so we start to see enterprises that are really sort of adopting that. We also see x86 platforms as that CPE being very high performance and fairly modest cost. I don't like to say low cost because we're not talking about a consumer grade device, but the price performance, or bang for buck in another way, is excellent at this point. We can get hundreds of megabits or gigabits out of a very small footprint CPE doing encryption at a customer site out of a device that basically is like a low-end netbook. So it's pretty neat. And that allows us to mix and match the capabilities of equipment and bandwidth and the requirements of a site. We get this flexibility in the middle, so we get service chaining, we get the centralization of configuration, so we can centralize these ACLs and PBR, and there's a disturbingly large amount of PBR and ACLs in these enterprise networks. But other places where there's a lot of ACLs and PBR are mobile networks, and deep inside carrier networks as well. So there's a lot of interest in being able to centralize this in the context of replacing or supplementing MPLS VPNs. Also wanting to be able to build hybrid clouds, where I have an on-premises or private cloud environment, and I want to shift VMs out into public cloud. And I need to dynamically build tunnels from my premises to different cloud providers and between cloud providers in order to have my Oracle database running in Amazon talking to one of my backends locally, which is talking to my Salesforce billing system. And then on the left-hand side, control. And that's management scale. So we've got some centralization of the management plane. I don't need to go and touch 10,000 devices if I'm a carrier managing 10,000. I have, and I'll explain this a little bit later, an implicit in-band management plane. But I've also got this more IT-centric approach as well, where I can do things through APIs. I'm not going into boxes and looking through these ACLs to find the right problem, or find the right ACL to fix the problem. And I can automate things pretty extensively. Upgrades, other events, bandwidth utilization, network failure management, etc. I get a lot more visibility and reporting. And that's really important as we're going into this ever-paranoid security world, where I need to be able to see what my network config and my ACLs look like on all of my devices and understand what's in line with my expectations and what's not. So how this starts to evolve a traditional L3 VPN network. So here on the left, we've got our MPLS environment, we've got some PEs, we've got a PEC link, and we've got a VRF. So we've got some fairly complex routing relationships today. If we have customers that are doing a lot of traffic engineering or have very large scale L3 VPNs, this can actually be a fun control plane challenge to scale. If we have low bandwidth links, then we tend to load up our PEs, and we need to have 10,000 BGP PE sessions. If we have high bandwidth links, then maybe we max out line cards before we max out BGP scale. But at the end of the day, the BGP process on our PEs is typically working quite hard. And that impacts our route engines or CPMs. It impacts our FIB scale as well. And we've also got to manage these routing policies. The service provider becomes really intimately involved in the customer's topology. So when I was in the Alcatel-Lucent 7750 team, one of our carrier customers provided L3 VPNs for an extremely large global bank. And that bank, their VRF ran about 100,000 routes. So when something in their network flapped, it could actually really hurt, depending on what flapped and where it was, and how in the customer's network they were tying different carriers together. So they became very, very involved, and scaling was always exciting. But it also means that if the bank came along and said, well, I need an extranet service, or I need this or that, I need to reconfigure how New Zealand talks to the US, there was a lot of manual operations that only the service provider could do. The customer couldn't just say, I want a sub-VPN between these sites, and I want it to only be controlled by Australia, New Zealand, and the US team. Or I can't delegate control to the voice team for just the voice network. So building smaller VPNs or micro VPNs was challenging. We also have limitations on how big our network is. If we have a customer that wants us to expand into Australia, then we're kind of going to have to expand into Australia or build complex NNIs and figure out how to tie the networks together. And that also brings us down to what's the most common feature set available on all of my PEs, on my global networks. So we go over to the other side and look at how things change a little bit. So the PE-CE relationship changes. The CE can become a completely stub device. It doesn't even need to run a routing protocol. Heck, it could sit on a broadband connection and just consume that and look like a typical IPOE broadband sub. We don't need those routing protocols. We can run them as options if we need to. We can integrate the controllers into the underlay network, so the controllers are underlay aware. We can then, we can add features into the underlays if we want to, or we can just have the controllers advertising routes into the underlay if that's needed. And the underlay sort of becomes unaware of the service layer. Just like the optical network no longer has any idea that this is a voice packet versus an internet packet, my transport network just sees IP. It doesn't really know or care that it's an IPsec or VXLAN or GRE packet that's in turn carrying another payload in it. So it becomes less service aware. So that means that we could build the underlay as a VRF still, or we could use anything. It could be a wireless connection, it could be a broadband connection, it could be all of the above, allowing us to mix and match parts of our network. And this gets kind of interesting. If I'm a service provider that today only offers broadband and not business services, but I want to offer business services, now I can do this without having to go and build a lot of PEs, possibly without even enabling MPLS in my network, just by overlaying on the transport that I've got. And we got some of these benefits of all the centralized control. And this allows us to scale things very large. So again, overlays are not new. Enterprises have been running site-to-site and full mesh VPNs for a very long time. But scaling those has been challenging. Pretty good visibility in the center and pushing out tunnel configuration to the devices makes sense. And it also allows us to build the appropriate level of meshiness. Maybe it makes sense for New Zealand to in cables so we can control our distribution and topologies. Also, we can manage very large-scale IPsec. We can centralize key generation and distribution. We can do hybrid key generation and distribution as well. These are all things that a lot of enterprises have been thinking about how to solve, and a lot of service providers have been thinking about how to solve. And where it also starts to get interesting is that sort of performance-aware routing. If I have an application that I recognize as high priority or important to me, I can designate that onto the link that performs best. So the controller has the visibility and can get the visibility of bandwidth and run OAM tests site to site, centralize that, and determine what kind of flow rules I need to push down to the CPEs in order to drive traffic around the network. So how does it work? I don't need to spend a lot of time here, but a quick recap, right? We separate out in an SDN environment the management and policy layer, the controller and forwarding engine, the operating system, and the hardware. This allows us to abstract things, allows us in some cases to swap out different modules, use different controllers, or use different forwarding engines, use different hardware, run on different operating systems. Putting it together, I've picked a couple of technologies. Obviously, I'm intimately familiar with one vendor's implementation, but you could mix and match here, right? EVPN is a BGP address family. It's been talked about at APRICOT by us, by other vendors for many years. And it's kind of a really exciting way of distributing both MAC and address reachability in service provider networks using BGP. VXLAN is a very commonly used data plane that we see really out of the data center world. It's an IP encapsulation, runs over UDP, allows us to carry a complete Ethernet frame inside UDP. You could use plenty of other NCAPs. You could use other BGP control planes or routing control planes as well. And just like Pete showed, we can take these controllers out of a router and think of it as this way. Previously, where we had the routers running BGP or OSPF and calculating a fib, pushing it to the line cards were our data path. We changed that model slightly. We have controllers running BGP, OSPF, other protocols like OpenFlow. And they can push that down. And OpenFlow is a really good way to use to push your fib information down to the CPEs, and then data plane CPE to CPE. So those routers don't go away. They're still there. We're just, instead of doing the NCAP or the primary service NCAP at the PE, and the routers and the PEs can further NCAP if they need to, or just treat it as IP. Whoa, that jumps forwards a bunch of slides. So, to look at it in a little bit, okay, it's all coming together now. So I've got my controllers sitting up there, I've got my CPEs, I've got an underlay, let's call it the internet, that's tying all of these sites together. I can push things down, the fib, to the CPEs. These CPEs could be virtual machines or x86, and we can build tunnels between the sites. Pretty clear so far. OpenFlow is an excellent way of doing this. There's other protocols out there, like OVSDB, obviously proprietary things. If we think about a classic chassis-based router, it's something proprietary between the control cards and the line cards. So people can do things different ways here. It could be BGP even. We could continue to run a BGP routing relationship there. We can push down the MAC or the IP or both address reachability information to these devices, and we become aware of which MAC address, which IP address, which subnet is reachable behind different devices. So just like in MPLS, we allocate a service label, a transport label. A transport label gives us the visibility of the next hop PE. We can do all of this, but we're just doing it with IP. So in my next slide, we look at these sites here. So on the underlay network, 192.0.2.1.2.3 are the uplink or outside IP addresses of the devices. These subnets are reachable behind them. We have a VXLAN tunnel which is going to be established between them, a stateless tunnel, so established is actually a poor choice of words by me. And we populate a fib which looks like this. Next hop 192.0.2.1, VNI whatever. We can also use the segment identifier for service chaining as well. We can then further encapsulate that inside IPsec for confidentiality, and that's a pretty common example in the SD-WAN use cases. So how does this change from the existing model, and why would we want to change it? Well, if we again look back at our traditional model with a VRF, we have these many provisioning touch points. We need to create a sub-interface, we have to assign a port, etc. And there could be many hops between the PE and the CPE, an aggregation network, a DSLAM, a GPON OLT, whatever's in between. We've got all these touch points out here. We need to get the routing relationship up and running, be it BGP or RIP if you really like to. So we've got to provision all of these things. We have to be concerned about the scalability of our PEs. We have to be concerned about how we handle failover, potentially all of the stuff and the impacts of redundancy in the aggregation networks, etc. It's actually quite complex, right, to provision an L3 VPN. It's really easy in a lab to build 2 sites and make a ping go past. But when you go and build an L3 VPN for a big enterprise with, say, even just 50 sites, it's actually a lot of engineering work. And some service providers have automated this, and we can cookie cutter it. Right? We can say, yes, I've got an L3 VPN type 2, build it. These are my 50 sites. But if you haven't got that level of automation, this configuration is lengthy, it's time-consuming, and it's error-prone. Furthermore, if the service provider is managing the CPE, or if the enterprise is managing the CPE, you have even more things to touch, configure, and potentially misconfigure. What we want to do is move to a one-time provisioning model where these PEs are very low touch, just like our optical networks in a service provider core are quite low touch now. We provision once, use many. So this could become more like a BNG or a BRAS here, and this guy becomes more like a broadband subscriber, or it could be really super templated, no routing relationships needed. Let's use the same /30 type examples to really template this up. We then move to dynamic service provisioning, where we have API interfaces here. We have a single, central point where we go and interrogate and ask about our network, configure our network. If a new site is coming online, we can push down the config to all of the devices in the network about that new site. And also, we can start to take advantage of that multipathing and using different parts of the networks. So really about simplifying that provisioning and activation. And in service provider land, this can be tens of thousands of dollars per site that's activated. If you remove that cost, obviously things get pretty interesting for your CFO. That traffic steering part is something that I see enterprises and I see carriers alike is very interested in. And the reason for that is obviously there's a lot of business up here. You know, there's billions and billions of dollars of business that's coming from these MPLS networks. If it all goes over here, there's a little bit of a shortfall, right? We don't quite get as much revenue as we used to. We also have enough enterprises that are quite conservative. They want to start with just moving some traffic over to an internet link. So if a service provider can say, hey guys, I can give you the right cost mix, the right service mix for your VPNs, I'll help you deploy these hybrid VPNs, and I can give you all of the tools that you need to move traffic between these links. So that's our policy-based routing. And PBR at large scale is a nightmare. So if we have rules that say things that look like voice need to be steered over the MPLS VPN link because it's guaranteed in SLAs, let's steer it over that link. If we have things that look like Facebook, let's steer them over the cheapest link. And this could even become, you know, a bring your own access kind of model where this is another ISP. And it could be many ISPs. And to steal a term from storage guys, just a bunch of disks, well, it becomes just a bunch of links. I want to measure the performance of the links, put the right traffic onto my different uplinks, and move traffic between links and, you know, try and get the best value I can. And this is something that SMEs have been doing for quite a while, and we've seen sort of, you know, high-end consumer-grade routers that have done this with NAT tricks, etc., to do all active uplinks. But we can do this much more efficiently. We can move traffic. We can, you know, be aware of bandwidth availability. We can use OAM, etc. There's a lot of things that you could do here with that centralized control plane. And finally, this brings us to some exciting things around service chaining. Pete, I think, touched on this pretty neatly. It's not always practical to put firewalls everywhere. We may want to push some of that firewall capability into the network forwarding engines. We might want to pass things through multiple types of security applications. So we typically see things like data loss prevention, you know, NAT devices, firewalls, etc. We can build ever more complex service chaining paths running through data centers on x86 systems and move traffic selectively through these devices based on rule sets. We can also do the traffic mirroring for analytics, etc. All of these things are very, very advantageous in service provider networks as well as enterprise networks. We can interwork things as well. You know, using things like EVPN, VXLAN, GRE means that we have a lot of ways of making the underlay service aware. You know, it's very difficult to move from a network that is already existing to a completely new design. We need to have midpoints, so you have to have interworking functions. We can do this, you know, quite classically, back-to-back PEs, quote unquote, or we could do some native interworking. And so this is where the selection of technology becomes pretty interesting. So, you know, off-the-shelf components out there, off-the-shelf technologies, this is all being done already in the data center networks. You know, if you think about this as a virtual machine and this is a data center gateway, we've been doing that for quite some time. Comparison there, if you've been listening, this should be fairly easy, so I'm going to skip it and just say, why do I care? I'm a service provider. This sounds like an enterprise problem. As a service provider, you probably actually have the same problems, but it's just your sales guys and maybe your provisioning team that hear about them rather than engineering and architecture. And that's because your enterprises have these problems and they want to do these things. But at the much more macro level, you still have an automation and a service and transport segmentation issue that you may or may not want to address. You may simply not care as well, and that's totally cool. You know, if you just want to be a bit carrier, that's fine. But if you want to get into, for instance, from the broadband market into offering business services, or if you want to sort of, you know, merge your data center and network functions and allow customers to tie things together on demand, then maybe this is a technology that you really want to be looking at. SD-WAN was basically unknown as an industry buzzword 18 months ago. It started booming last year, and there is a huge amount of venture capital and interest in this at this point. In the Bay Area, it's just crazy with the number of SD-WAN vendors. This isn't something that's particularly unique or special about Nuage or Juniper or Cisco or Brocade or any of the typical big vendors. There is so much sort of business going on out there with enterprises all looking at these problems and how they solve them. There's a lot of interesting stuff that I think can be applied in the service provider networks. A lot of stuff that we've talked about to solve other problems, like Shaowen talked about, like Pete talked about, like Eddie's actually talked about in the past as well. These are all pretty cool things that we can do to build new VPNs. So I think it's really interesting to care about this and look at how you can run new services more efficiently and potentially get some new revenue or protect existing revenue. So in conclusion, proven deployments. This is out there. There are enterprises running it themselves. There are carriers running it. It's not just experiments anymore. It's deployed, again, I wouldn't say at massive scale, but moderate scale. I'm working with some operators that are doing hundreds of sites in a VPN using this technology now, and looking to start scaling this year to thousands of sites in a VPN, etc. Overlays aren't new. And the service layer overlay is really a natural evolution. We can look at segment routing staying in the core so that our PEs have a traffic engineering capability, but we just move the service layer a little bit further out and we could do it from a CPE, virtual, physical, or wherever we want to place it. So it's really about that speed, flexibility, and optimization of the network service delivery. So we're right on time for lunch. So thank you for listening. If you want to see it in action, we have a demo out there and you can ask me questions.
Hey, Rich Bayless from Juniper. This came up in Paris last year. I just wanted to go back. Also in terms of, you made some bold claims around simplicity by removing a lot of useful functionality from the network. Let me start on simplicity. In a full mesh network, moving the VRF to a VXLAN overlay would essentially mean that you may need to provision VXLAN for a full mesh on every single one of your CPEs.
Yep.
Is it really simpler to configure 5,000 VXLAN tunnels over GRE from every CPE to every other CPE?
Well, that's where that whole orchestration layer comes in, right? It's not a case of I'm going to go and configure 5,000 tunnels. That's an existing problem for overlay networks.
So a orchestration system solves the fact that you've added huge complexity to the CPE?
Yes, it does. And I wouldn't say it's adding complexity to the CPE, but at the same time, we've moved that out of the PE. We're already doing this for a large VRF, right, on a PE.
There's not 5,000 tunnels in a VRF.
Okay, typically not 5,000, but if you've got a fairly large global VPN, you're going to be hiding some of the topologies in your network.
On the removal of VRFs, one of the challenges with that is that VRFs provide a very neat way of providing separation of traffic.
Yep.
So in terms of providing what essentially sounds like an IP backbone underlay for your architecture, firstly, is it realistic to assume that customers aren't going to run routing protocols? And secondly, does that provide some form of security hole if you have customers sharing an IP backbone, which is what we had before MPLS came along, and it was a terrible, terrible nightmare?
Well, I guess that depends on your perspective of sharing the network, right? Like today, if I'm running internet in a VRF, I probably have congestion and denial of service issues. No amount of VRFs is going to solve the fact that I can congest a P2P link if it's a shared PE. Same with a customer potentially doing something stupid and taking down their VRF, which has flow-on impacts elsewhere in the PE. But I agree with you. It is an interesting challenge if I'm saying, yep, let's get rid of VRFs for customer segmentation and move all of our traffic over a shared underlay. Now, that doesn't have to be the case, right? The main requirement from ONUG is that I can mix and match private and public transport. And the public transport requirement is typically driven by cost, and that's usually saying, I want to put my low-value traffic there. I may still, if I'm an enterprise, I may still retain an MPLS VRF. If I'm a service provider, I may still use VRFs.
Yeah, but so specifically on that, when you say you may still, in the use case where you don't still use a VRF and you remove VRFs, are you confident that it's actually secure to do that?
I think it's the same level of confidence for any other internet-based transport.
So it's internet security?
It is internet-level security, yes.
Okay, thank you.
Thank you.